Right, going on to parametric integration. Now, I didn't teach you guys any parametric equations, so I'm going to assume that you are pretty okay with it as we move into this. It's going to be a bit wordy, I'm afraid to say. So here we go. The area for the parametric traditionally is always some function which we can write as f of x or g of x, but you can also write it as y for whatever your equation is, and then of course we have a dx. This is your normal Cartesian formula, okay? But for parametric we're going to keep this y, but this here, because obviously parametrics use the letter t in it, what we can do is replace this dx with dx divided by dt. There's a hint. And then actually our equivalent of dx is dt. This is not in the formula book, so this form you would need to remember. Now it will make more sense when we actually do it, but first of all we've got to set up an equation anyway for us all. So starting off, we're going to have, given the curve, if I was with you we'd have had this on some note sheets, can't be helped. So given the curve with parametric equations of x equals t squared plus 1 and y equals t add 2. Don't need to do anything fantastic to get these ideas over, and we're going to do it for the limit of 1 and t and 4. So t is going to be between and equal to 1 and 4. The first thing we're going to do, so you can really see what's going on, is of course we're going to sketch the curve. Now, I don't know how you guys would have done this, but I've always done it where we'll have a t value and an x value and a y value, and then I'm just going to do the integers 1, 2, 3 and 4, so I'm not going to do anything fancy here either. And if I put t into this, we'll get 2, 5, 10 and 17. And if I put these t values into the y equation, we'll just get 3, 4, 5 and 6. And then when we sketch it, well, it's not really anything much. It's not a fantastically pretty one or anything like that. It's literally going to be a bit like so. This value here, let me just extend that y-axis, this value here is obviously for x equals 2, and this value here is for 17, this is my x-axis here, and then this is 3, and going across. I know I've not really done it very well to scale at all, have I? And then I can say this is t equals 1, and this is t equals 4, and obviously you probably have t equals 3, and t equals 2, slotting around in there. Right, so what we're going to do is find the area between the curve and the x-axis. Okay, calculate the area between x equals 2, x equals 17, between the curve and the x-axis. Okay. So what we are doing is we are looking at actually finding this area just here. Now, as I said, what could I have done with having a bit more room? Never mind. As I said, the formula we are using is y. We want dx by dt, and then we're going to integrate it according to dt. But you can, if you wanted to, because it's a fairly straightforward one, you could put these two together, have a nice curve, integrate that normally, but really most of the time, unless you want to start introducing square roots and things, which actually isn't a very good idea, because the whole, is it a plus, is it a minus? The idea with the parametrics is that they become very difficult to put together to then have something which you can easily integrate. The idea behind using this is that actually putting these two together instead gives you an equation which you can integrate much more easily. So, because it's t values that you're going to end up with, and you'll see what I mean when I put it together here, we're actually going to integrate it between these two t values here, 1 and 4. Okay, that's the plan. So, the y equation was t add 2. I'm going to put it in a bracket just here, t add 2. I'm going to be multiplying it by dx by dt. So, dx by dt, this differentiated is just 2t. So I've got to times this here by 2t, and then I'm integrating it according to t. So as you can see, I've now got an equation that's only got the letters t in it. There's no point doing x equals 2 and x equals 17 as your limits. It's not going to work. So, multiply out the bracket. T times 2t is of course 2t squared. 2 times 2t is 4t dt. Integrating that, so 2t squared will integrate to 2t cubed over 3. So, equals square bracket 2t cubed over 3 plus 4t will integrate to 2t squared, and again the t values were between 4 and 1. So I'm going to stick 4 into it, give myself a bit more room. 4 cubed is 64, times 2 is 128, so it's 128 over 3. And then 4 squared is 16, times 2 is 32. Then put 1 into it, will give us 2 over 3 plus 2. And then, for some reason, I do not have a final answer on my notes. Do have to excuse me, just picking up the calculator. It's very remiss of me, isn't it? So 128 over 3. Yeah, just twiddle your thumbs while you're waiting for me to stick this into the calculator. 2 over 3 plus 2. Maybe it's one of those things which when I do it in class I then get students to do. Who knows? It gives me an answer of 72. If you want to check it, corrections on a postcard, you know, lovely, good, right. I'm gonna do another equation then, this time. We are going to have a curve has parametric equations. Of x equals t squared plus 1 and y equals t cubed minus 4t, and this time the domain of t is between minus 2 and 2. And again we're going to sketch the curve. have to excuse me, I know I've only got 15 minutes on each of these videos, so I have to go at a bit of a lick. So t, x and y, this time between -2, -1, 0, 1 and 2. And when you stick it into the different equations, your x values are going to be 5, 2, 1, 2 and 5, and your y values will be 0, 3, 0, -3 and 0. Got a bit of shaking with the camera tonight because of how I've had to position it. Right, so when you sketch it, you end up with a curve that looks, it's meant to be more symmetrical than that, I apologise. Curve that looks like this. This here is t equals plus and minus 2. This one here is when t equals 0. We have t equals -1 up here. It's the negative t value gives a positive y value, and this is t equals 1 just here. And then if you want to, you can go across and say this is the value of 3, and this here is the value -3. And then the bit that we are going to find is the area that is enclosed by the curve. Okay, so part B is going to be find area enclosed by the curve. Now this one is slightly more awkward because when you do it, we've got to do the top equation, the top part of the equation, which is between -2 and 0, and then we're going to have to do the bottom bit between +2 and 0, because these values here on the bottom, these are the positive t values. So what I am saying is that we are going to be integrating between -2 and 0 dt plus, and then we're going to do it between +2 and 0 dt. Okay, that's the plan. So again, we are looking at doing y dx by dt and it's going to equal, so the y equation was t cubed take away 40, dx by dt is going to be 2t, I'm not going to put the limits on at this point. Multiplying it out gives me 2t to the 4 minus 8t squared, and then we're going to integrate, so 2t to the 5 over 5 minus 8t cubed over 3 like so. And then I'm going to put on here at this point, I'm going to say between -2 and 0, and then I'm going to rewrite it again as 2t5 over 5 minus 8t cubed over 3 between 2 and 0. Sorry, I caught the camera. Slight error on my part. Because this bit here, between the positive t values is underneath the curve, this should actually be the 0 just here, and this should be the 2. Sorry, let's just cross that out and do that better. So, I'm running out of time. This bit here, when you plug it in, will give you 128 over 5. Oh dear, the pens are starting to run out. And then obviously minus 0. Oh, it has started to run out. What's just gone on there? and then this one here, when you put the 0 in, obviously will give you 0, then you do the minus for it. When you put the 2 in, it will give you minus 128 over 5. Okay, and then whack it into the calculator, you will get 256 over 15 as your final area.